quite happy to say that the standard model of particle physics is a metaphor. I've got no trouble with that language. I would insist on the caveat that it's the single greatest metaphor in the history of human civilization.
I believe physics explains everything, even love, everything. It's just very complicated. And it's not really the task of physics. You don't call it physics, and it's a completely stupid idea.
I don't think that the world ultimately consists of atoms and electrons or quarks and bosons, or that the conceptual objects, things like space and time or quantum waves, are somehow real things out there in the world.
We're going to look at one of the most important touching points that there is in the human endeavour, which is the relationship between imagination and creativity and the real world that we touch. So uncovering reality is all about looking at whether science really does describe reality or how much of it's in our heads. My brief says that physics depends on the correspondence between mathematical laws and the world. But the question we want to address here is, does it? Are the models that we use powerful tools, or do they actually exist out there in nature? And how much of our description of the universe actually enables us to understand what's really there?
Firstly, let me just make a confession. Physics and physicists are pretty limited in the kinds of things we can describe, or at least describe usefully. You know, when things get too complicated, we kind of get a bit scared. We can't solve the equations. We don't really know what to do. You know, anything on the level of human interactions or problems in society, anything that's just hard, we're not good at solving. Okay? What we're good at is when we can find situations where you can sweep away those complications, and you can focus in on the essence of something. So try to isolate something, and that's where we can really make progress. So there's sort of a two-pronged attack we have on understanding the world. The first, I guess, is what you would call fundamental physics. So it's where you just look at smaller and smaller distance scales and try to understand what everything's made of and then what that stuff does. That's sort of the first approach. And I think on this level, physics has just been spectacularly successful. You know, this is the story of atoms in the periodic table, or in the more modern perspective, particle physics and what's called the standard model. It's our best theory for everything that we have. And these theories are just amazing. We have the standard model. We've had it for 30 years. It's survived everything we've thrown at it. It predicts correctly every single experiment that we've been able to do, and very often with an accuracy that's just unprecedented in any other field of human endeavor. You know, to 9 decimal places, 9 digits after the decimal point. We'll do the calculations and it'll just be right. So, this is just very, very impressive. Okay, so that's the first approach of physics. The second approach is actually what most physicists do most of the time, which is try to work backwards. So try to start with those building blocks that we've discovered, typically atoms and electrons, and then try to work sort of up in the hierarchy to understand all the things that we missed in our rush to get to the very bottom. So here I think it's a little more of a mixed bag. It's hard to do that. In particular, because what happens is you find that when you take billions of particles and you put them together, they exhibit phenomena that you don't see for a single particle. They exhibit what's called emergent phenomena. You get collective behavior with all of these particles cooperating together to give rise to new building blocks on the next level that you probably wouldn't have thought of. They're certainly not obvious by looking at the fundamental laws of physics. So here, as I said, things are a little more rocky. There's some areas of science that I think we've just nailed. Chemistry. Chemistry can basically be understood in terms of physics and understood at a quantitative level. Material science is what's called condensed matter physics, but understanding why the wood looks like it does, why the light shines off the glass but not off the wood, things like this, why metals conduct electricity. And that, again, we've nailed it. But then as things start to get messier, as you get to molecular biology, we start to struggle. As we get to cellular biology, we're really in trouble. You know, as you move up, as you get to physiology or human psychology or social sciences, you know, we're really way out of our depth here. So that's sort of my global vision of physics. It's limited in what it can say about the world, but when it's good, it's just really, really good. When you're in the realm where physics is effective, I just think there's no other game in town. You know, this is far and away the best thing that we have to describe reality at those levels.
I understood that this is, we have to describe reality. And this was really the reason why I'm a scientist. Because the whole idea of being a scientist, if I understand what's going on, this is what I get out of my work. This is my purpose. And if I go to deep down and see quarks and see standard model, I see we have, as we said, it's beautifully correct. When I go to language of mathematics, it's very elegant, it's very simple. But my main work is foundations of quantum mechanics. It's when I start to use these basic laws of physics, which work perfectly for very small systems, and try to go up. Now, there are this chemistry, biology, whatever, when we can use physics and try to explain things, and things are messy, and I don't know exactly what's going on. But I tend to believe that it will work fine. What I'm looking for, being in the foundations, and there is such an area as foundations of quantum mechanics, foundations of physics today, is the places where there are paradoxes. Sometimes you take these basic, simple laws, you apply them, and you can apply them to a system which you can really see, and you get to a paradoxes. This is a situation which I consider. Like you mentioned this interaction-free measurement, I'm trying to find an object without touching it. It contradicts our common sense. In my work, I'm looking for paradoxes, but not to find that nature is strange. I'm looking to paradoxes to solve them, because my final idea to get the complete simple explanation. And I believe that there is one. I have to admit that the position which I have about reality, it's not what we usually see around. I believe that the reality is not kind of strong object as we see here. The reality, everything is wave. This is the only way where I can have a theory which I can understand everything. Everything is just wave. Wave which have interference, and moreover, it's a quantum wave. Quantum wave have not more just interference, it has entanglement. Like different particles can be entangled and interfere only when they are together. I have to pay a price, which I mentioned in the 2 hours ago when I talked about causality, because explain reality, explain causality. To get a correct explanation of this picture, I have to admit that what I see here, it's not the only thing which there is there. There should be some many parallel worlds in which maybe I'm not here and you didn't come to this Hay Festival. Now, it's not that everything exists. Sometimes I can make things to split. In my homepage, I have a word splitter. You can take my name, look on internet, go to word splitter, and make a split of word to any from 2 to 6. And then you decide where you go every time. And you will be sure that some of copy of you will go to all these places. I believe in all these strange things because I want to have a simple explanation of everything which I see. And I believe that today's physics has a very good explanation. All what we see around, we understand. There are people like you working in string theory and other things. These are things which you cannot really measure now. We also want to understand the beginning of the universe and the end. I believe that there will be no more evolutions when you'll finish your job. I believe that now, roughly, we understand everything which is around.
On the one hand, I'm in the lion's den here with two realist scientists, but in some ways, I don't differ in terms of what I would be wanting to do from what Lev just said. I would be wanting to describe how the world is and say as much about what is going on as we can. And that's what I understood philosophy to be attempting to do. So we start from some common ground. However, scientific theories, like all of our accounts of the world, are created by the mind. And that, I guess, we can all agree. But I don't think that they describe the world itself. I think they are ways that we use to make sense of the world and to intervene, and they're enormously powerful and successful. But I don't think that in some sense they say how it is. And I mean that at a quite straightforward level. I don't think that the world ultimately consists of atoms and electrons or quarks and bosons, or that the conceptual objects, things like space and time or quantum waves, are somehow real things out there in the world. Now, I don't say this because I'm some sort of romantic mystic that wants to imagine that the world is some ineffable other that we can't get at. I say this because I think that the alternative, which is the idea that our theories describe the world exactly, is based on a mistake. It's based on the mistake of realism, which is incoherent and which is also damaging. I think if we abandoned realism, we would make our science stronger and more powerful, not weaker. So I don't put forward this in some attempt to say there's some alternative framework of talking which is either romantic or mystical as an alternative to science. I'm wanting to be more rigorous and, in a sense, more scientific about thinking how we might get there. Now, let me just say, first of all, because I'm often misunderstood, I'm not saying that the world doesn't exist, that somehow that it's all just an illusion. The world, whatever it is, the stuff there, certainly is there. I'm not in some crazed philosopher position of imagining it's all in our heads. And nor am I saying that we can create whatever we want, that our accounts of the world, our theories of the world, just spin free somehow, that there's no constraint on why we hold them. But I do not think that those two thoughts lead to the conclusion that there's some direct mapping between the way that we think and the way the world is, let alone a one-to-one mapping. Now, you might say, well, it's all very well, Hilary, but how do they work in that case? Because they're fantastically powerful. And I accept, of course, they're fantastically powerful. Indeed, I'd like to make them more powerful. How do they work? Well, we don't need one-to-one mapping to make theories work. It would take me a while to really convince you, because this is embedded in the way that all of us think. And science is just an elaboration of that everyday assumption. But to give you an indication of what I might mean by that, if you look up at the stars and you see a shape, you might say, oh, well, look, I can see the shape of a rose, or I can see the shape of an umbrella. Now, you could see an indefinite number of shapes up there in the stars, an infinite number of shapes. There's nothing in connection between those shapes and the stars. They're a way of holding those stars, but no one would say, well, that's actually a rose or actually an umbrella. That doesn't mean to say that it isn't useful. You can say, having identified a group of stars as a rose, you can say, look at the star that's just to the right of the top petal. You can track the rose across the sky. You can say, it goes that way, it doesn't go this way. you can refine your account. You can say, actually, it's not, it may not appear to be a rose because there are no thorns on the stem, but if you imagine that the thorn is on the side that we can't see, so you can refine your way of holding that bit of the stars in order to fit what you get. And if you patterned the whole of the sky with these ways of holding the stars, you might identify those bits that don't fit into the patterns, what we now call planets. And you would be able to use all of those together to navigate the seas. So don't imagine that you need one-to-one mapping, or indeed a mapping of any sort, for the theory to work, or for the theory to be modified in the light of what takes place. Now, I want to propose, therefore, that we think of the world as not being made of lots of little bits that we might get the correct answer to, because I don't think there are any little bits. In fact, I think those little bits are a function of the structure of our thought and the structure of our language. One of the characteristics of the way that we hold the world is we close the openness of the world. I can't tell you what the world is like because it's outside of thought and language. I can only use thought and language to talk to you. So I will use the frameworks and structures of thought and language to tell you what I might think is going on. But let's imagine that we think of the world as being open, therefore, because I can't say how it is. What we do as humans is we close the openness of the world into particularities. We take all of this stuff and we make it into bits. And we do that right from the outset, from the photoreceptors in our eye. The photoreceptor fires, we have one bit, the firing of the neuron. The firing of the neuron is not out there in the world. No one would suggest that the firing of the neuron is the same thing as the world. We've just taken all of the world and we turned it into one thing, the firing of the photoreceptor. And that happens at lots of layers in the brain processes. So we hold the world as these particulars, and they enable us to intervene. The firing of the photoreceptor enables the system to make some judgments about how to intervene. But there isn't somehow a firing of a photoreceptor out there in the universe. It's a response. It's a causal response. Our ideas about the universe are causal responses to the universe. And we use those ideas to intervene in the world, and we can correct them and make them better, and I would want us to carry on making them better. But there are certain essential characteristics of our thought which can mislead us into thinking we've got somewhere. So we can take any particular that we create in our thought and language, and we can always ask what's in that and find more bits. And then we can find out what's more bits in those. So we get more and more particulars. We're never going to get to the bottom of that. There are always going to be more bits. But that's not because there are more bits out there in the world. It's because that's how our thought and language function. We divide the worlds into bits in order to make sense of it. So, of course, we find bits, and the more bits we look for, the more we can find. And the number of bits in the current scientific story is just vast. It's so vast, you can't comprehend it. Not only there are all of the particles now, of course, but all of the particles have forces which affect every other particle in the universe, and they're all bits according to the Standard Model. And now we have lots of bits in the sort of infinite numbers of other universes, all of whom have more bits. Well, I'm not saying that those models might not be useful, but let's not imagine that those bits are somehow ultimately there. They're ways of enabling us to intervene.
An impassioned exposition of the idea, and in comparison with which realism is incoherent and damaging, and if you abandoned it, you could do much better science. David, what do you think about that?
I'd like to pull Hilary up on something at the end, that the number of bits we have in the universe is vast. The number of particles, fundamental particles, that we currently have in our models is 12. Which is a big number, but not vast. The number of forces we have connecting these is 4, and these 4 forces fit together with the 12 particles in what's called the Standard Model, in what, to my mind, is the most perfect, beautiful jigsaw imaginable. And some people say the Standard Model is ugly. I don't think this is true at all. I think it's a wonderful piece of mathematics. So I'm not saying the Standard Model is the end. It's certainly not. It's certainly an approximation. I'm not even sure if there is an end. I'm guessing Hilary would say no. There's no
Therefore I say
fundamental
yes.
theory of everything. I don't know if that's true
And
or not.
indeed,
That
I
might
think-
be true.
I'd go a bit further. I'd say it's an absurd idea. I mean, just imagine we got to the end. Would we close down the Large Hadron Collider? Would we stop all of our universities exploring? No, you smile, because it's obviously not going to happen. I'd take anyone on, Stephen Hawking said, well, we're really very nearly the end. At the end of the 19th century, we're very nearly the end. Everyone always thinks that we're very nearly the end. That's because of the structure of closure.
Hilary.
The way that we think gives us the impression that we're very nearly the end, but we're never even close. It's a way of holding.
So let's hear, because Lev actually
we
specifically
cannot
mentioned
be
this.
sure
Let's hear
that
from
we
him.
are close, but it might be that we are there. I think you count 4, I think it's 3, electromagnetic and weak, I will put together. So the number of laws is very small, the physics is extremely elegant. It tells us almost everything. Now, in a sense, in one thing I might agree in the following. What I'm looking is an ontology and mathematical theory of ontology. So I believe everything is this big wave with these 3 forces evolving according to laws of these 3 forces. But this big wave doesn't look like what we see here. We have to work hard to make a correspondence between this ontology, which I believe is there and we understand it. We will never know that we understand everything, but we can imagine that it is so, and we might have no signs that something wrong with it. But the correspondence is really difficult. To find a correspondence to our experience, there are infinite ways to find this correspondence. One will see it as a rose, and another see it as a cow or something else. So there are this infinity, and maybe we can improve it more and more. This part, correspondence of the ontology, which I think is, we are close to it, and this is finite and understandable. But corresponding to our experience, this is infinite. We can think all kinds of things. We can make poetry, other things, feelings. It's not beyond physics. I believe physics explains everything, even love, everything. It's just very complicated. And it's not really the task of physics. You don't call it physics, and it's a completely stupid idea to try to explain it with physics. This is not physics. So this other part of science is infinite. But the science itself, which tells us what's the ontology, I think it's rigid and understandable. And I feel that physics explains reality well.
So in that sense, you would say that there were vibrating strings out there in the real world that make up the particles that are out there in the real world, that behave in this way with the waves in the real world. And when you look at us, you see a combination of all of that. And then you're relating to it as something that's more constructed by you, but the strings are really out there.
If I just want to be trustful, I don't understand much about these vibrating strings. I'm working in foundations of quantum mechanics, which really responsible for essentially almost everything which we see around. Strings tells about some other things, and I'm not a specialist. My theory, which is explaining quantum mechanics, is such that it's relativistically covariant. It can go to strings. I have hope that nothing dramatic will happen when you go to strings. So what I do know, it's about the wave function which explains this. Everything, glasses, light, everything, all our feeling, all our senses. Here I think we are very on a strong ground that we understand essentially. I believe 100%. I never be known, cannot be sure, but I believe we understand 100% of this physics.
So in that case, Hilary, I guess that would mean that there's an edge to reality, that these particles are really out there, that they really behave in the ways that Lev is describing, but the way that we interact with them and interpret them and relate to them is something that's more, I won't use the word ineffable, but something that's more related to who we are and how we approach them, more like you're looking at the roses. What would you say to this?
We obviously just hold a different notion of the relationship between our theories and the world. Lev believes that our theories can describe how the world ultimately is. I would say that one of the difficulties for a realist perspective like that is how do you account for the theory itself? The theory is a product of the brain, so it's presumably the outcome of some processes in the brain. So the theories that Lev would have about the world would have to be somehow a mirror of the structure of the universe, which happens to appear in one part of the universe when he thinks it. Those sorts of puzzles are part of the puzzles of realism. I don't particularly want to pursue that puzzle. It's just that I think there are self-referential flaws in realism which you simply can't overcome. And it is indeed as a result of identifying the self-referential puzzles in realism that I think we have to look to what is initially a more implausible story, because we are all operate in a realist framework in everyday life of just thinking there are chairs and tables and houses and whatever. So the idea that it's not like that is initially counterintuitive, but I think we have to consider that because I think that the structure of realism simply doesn't work, and you can't make it work.
You described it as incoherent and actually damaging. So in what sense do you feel it's damaging to
Well, I think the
understanding
sense
of
in
the
which
universe?
it's damaging is that, and I think there's a noticeable shift in Stephen Hawking's description of this. I mean, maybe I'm wrong in saying that, but obviously in his sort of popular book, The Brief History of Time, he ends with saying, you know, maybe we are close to the mind of God or something, by which, of course, he meant that science might describe once and for all a grand unified theory of everything, sort of a thing. And now he seems to be more in a mode of talking about, well, we might find a better model, a more powerful model. Now, those are quite different versions. If you think that physics is operating within frames of thought, are models, and that those can be explored, and you can get further with them, and you can make a better one or a worse one, but there's no ultimate model, there are different ways of holding it, then I think that can be a very constructive way of doing it. And instead of thinking, you know, is there a right story here? Is it strings, or is it multiverses, or whatever is the frame? If you say, well, we could hold it like this. We could hold the world as if it was strings. And let's operate within that framework and see what the implications of that are. And you can always hold on to a theory. You can always, I mean, when Newton, I mean, it's Newton all of this stuff comes from, of course, the basic structure of force and acceleration. And it all comes from that, which was a brilliant mathematical frame. And when he first proposed this, the people initially said, it was all very well, this, Isaac, but you know, there are lots of things it doesn't explain. I mean, you know, the apple may fall off the tree because of gravity, but most of them are staying on the tree. And why is that? You say, well, there's an equal and opposite force. And they said, but this is circular. Any example I show you of something that is not doing what you said it was going to do, you create a new force. And then you operate some mathematics in order to account for why that works, which is what we still do. So indeed, the whole stuff about dark energy is, well, we've got a circumstance in which we propose the Big Bang and to account for the red shift and the apparent expansion of the universe. And then we discovered a little while ago that it's not just that the stars are moving away from us, but they're accelerating away from us. And that doesn't seem to be the outcome of a bang. It must be something pushing them. And so what's going on here? Oh, well, there must be an additional force which we're not aware of. So we go looking for it. Well, that's a great way of modifying your model. And you can patch your model. You can always patch your model. You can always come up with a way of why this works and patch it. And that patching is a good thing. Because there isn't an ultimate one. It's a good thing. You patch it and you try and get that to work, and then your model will work a bit better. But let's not imagine the model is the world.
But then
you can have a radically different one, which, I mean, for the farmer up the road who's an apple farmer and they're trying to work out what they should do, consulting physics as to when the apple's going to fall from the tree, it's just not a very good model. It's much better to say, oh, I've spoken to a lot of apple farmers, you know, it's usually around sort of mid-September, and if you get a bad bit, that's when they fall. Well, that's the right model to use.
But that doesn't mean that there isn't some fundamental reality inside the apples that is made up of atoms or is made up of nuclei. Or so I can see different ways of approaching how you handle the models you've got, but it doesn't mean that there isn't some reality out there.
Well,
maybe I can address.
You'd have to
Let me
explain
come
how
to
those
David.
models create those realities in that case.
Maybe I'll address some of these issues.
This is
We've got
physics as
strings,
metaphor,
we've
right?
got Newton, we've got dark energy, and I could tell you about all of them. I'll stick with Newton, though, because he's the simplest. So it's true that during Newton's time, people did argue that this theory was circular. They argued that this was a tautology. But this was also refuted during Newton's time. And what happened historically is the fact that Newton's theory was flexible.
How was it refuted?
I'll tell you. The fact that Newton's theory was flexible, the fact that it could accommodate new phenomena, was actually extraordinarily useful. It allowed us to discover facets of the electric force, magnetic forces, and so on. The way it's refuted is probably best seen from a modern perspective, which is just that it's wrong. And Newton's formulation was flexible, but it wasn't infinitely flexible. There are certain phenomena that you see in nature that can't be described by the equation F equals ma. And it's been found wrong on at least 3 occasions. Once by Faraday, who realized you had to add electric and magnetic fields. Once by Einstein, who realized that the laws of space and time needed changing in order to accommodate this equation. And once by people like Schrödinger and Heisenberg and others who had to turn to quantum mechanics. So this theory isn't a tautology. This theory is good, falsifiable science, and in fact, it's falsified science. So, it's a model that couldn't be patched up, and at some point, you have to go beyond. I could tell you something similar about dark energy. And the Big Bang was a particular model, and it broke down. It has kind of been patched by dark energy. So for those of you who don't know, we now know that 70% of the energy of the universe is what we call dark energy. And it's weird, and there's no two ways about it. It's an anti-gravity force field which is spread thinly throughout all of space and is making all the galaxies repel each other. So the universe is expanding, but the expansion is actually speeding up. It's a bit strange. But it's true, and it's true because we can see it. You can look out into space. You can see how fast those stars are moving away, and how fast they were moving away in the past. You can just see that it's speeding up.
When you say,
wait, sorry, hang on.
Sorry.
So we just need to take Soler.
First, just to comment, I believe F equal ma is correct. Always.
Yeah?
So I believe that, again, clearly that by the electromagnetic forces, some other forces, I believe that everything can be explained by local forces.
But that's true. But that's not F equals ma, right? Quantum mechanics is needed as well. You wouldn't disagree
quantum
with
mechanics, we have waves, and these localized wave packets, or part of the waves, move according to these forces.
In some approximation.
But you're right in the sense that today there is no such theory. This is a theory which I said that physics is finished, but I am looking for one. It's quantum mechanics F equal ma. There is no such thing today, but I believe it should be, because I believe in locality. And today quantum mechanics, as is built, it's built on potential and other things which are non-local concepts.
So that brings us...
But I wanted maybe to relate to the problem which you see, that we cannot explain what we self-reference and other things. I see analogy to Russell paradox. We had mathematics, which mathematics, pure mathematics is a set theory of sets. And Russell, in fact, showed he was a specialist in this theory. And then he found a paradox saying that the whole theory is wrong. He found a paradox. What kind of really self-reference? When you look on set, which is too big, then our normal things are kind of do not work. So when we consider very big things, I think it's difficult. We have to, mathematicians today saying everything is okay. We have to be careful. We have to limit ourselves. And then we can work with mathematics. My purpose is limited. I want to have a box of particles and maybe like our room. So I understand everything inside this room. I don't think we can talk about the whole universe, because then really there are all these self-reference problems and our language will not be appropriate. And these problems, dark energy, we don't have a laboratory really to test it. We don't know. We have a laboratory to test what's going on the table. If I have a good physical laws which explain everything which I see in the laboratory, I can extrapolate that there will be no problem with cosmology, because in cosmology there are so many unknown things. We don't have really much data. When we'll understand.
It's a domestic point of view, right? That if you've got everything on the table, that's all you need.
It's just a humble point of view there too, isn't it? It's sort of saying that if we limit our scope to something that's a little bit more humble than the grand scheme of understanding the entire universe, then maybe we'll get somewhere. However...
But I think, interesting, I think you're right that the Russell's paradox is relevant to that particular paradox, and indeed was influential in my case in forcing me to consider how one might try and overcome it. But I think that the idea that we can just give up talking about the big things and let's just deal with the little ones, I don't think is a plausible thing to do. Because in fact, you have that big story, whether you like it or not. You just operate with it, even though you know it's paradoxical. And instead, I think that's why initially I was forced into considering what initially seemed to me to be a completely implausible idea, that the world was nothing in particular. And think, let's operate within that model. Let's imagine that it's not already divided into lots of bits. How can we account for the fact that we're so able to intervene in it and understand it and so forth? And then I engaged in a process to try and understand what the structure of that might be in order to be able to make it work. And what I discovered was that you can account for its effectiveness much more easily than you might first appear. That you don't need this one-to-one mapping. And therefore, that the frameworks that we build are, to come to the point that David was saying, I think that when you say it's true that there is dark matter,
Dark energy.
Dark energy, sorry.
Dark matter's true as well, though.
Sorry, yeah. If you say it's true that there is dark energy, well, it's a necessary requirement at the moment to account for the accelerating universe. And that's why we hold it as being true, because it enables us to fit in with an empirical observation which was otherwise a fundamental problem for the Big Bang. Fine. I'm all in favor of that within that model. And maybe that model would turn out to be enormously valuable. And insofar it is valuable, I will be there with you saying, actually, maybe there's a problem in this bit. Maybe we should refine this bit. But I want to say, you don't need to have this metaphysical notion that you've somehow uncovered the nature of the world. What you have done is to modify your frame, your model, what I would call your closure. You modify your closure in order to make it work better. But you don't need this idea that somehow you've uncovered the ultimate. And indeed, the idea that you have, I think, generates, it doesn't allow you to say, actually, this model's just got too messy.
Can I just follow?
I can patch it here and I can patch it there. But in fact, the current model, you'd say it's fantastically simple. It's a lot more complicated than the Newtonian model. And the notion that there are an infinite number of other universes and there are these 12 basic particles and it's just not straightforward.
Let's just go with that. Let's just let David go with that.
So I think there's a case for thinking this has just got too complicated. Let's step back. Let's try a different way of holding things.
So this is science as metaphor, and also letting go of, looking at the world in a way that doesn't seem reasonable. But Einstein did that. As soon as he let go of the notion that rulers always had to be the same length and time clocks always had to tick at the same rate, he uncovered something that was much more interesting and much more useful, right? So why do you need to have that fundamental reality? Why can't you just let scientific theories be metaphors and not have to have that one-to-one mapping?
I'm quite happy to say that the standard model of particle physics is a metaphor. I've got no trouble with that language. I would insist on the caveat that it's the single greatest metaphor in the history of human civilization.
Well, we all like our own metaphors.
It's true. But this idea that that there's different ways of looking at the world and different ways can be useful. On the level of basic human experience, I agree. This is a very important fact of life, and it's a way in which you can make progress by accommodating different people's points of view, if you like. But when you get down to microscopic levels, we don't know of any other models. So we're arguing about whether or not there's a model that no one's ever discovered or can really talk about. And the bit of evidence that I think is there that says that there isn't any other model, that we've got it, we've nailed it, is that if you were to give me an atom, for example, so something very, very small, I can tell you in advance what will happen whatever you do to that atom, and with ridiculous precision. When you get down to smaller, when you get down to quarks, or you get down to the Higgs boson we've just discovered, the Higgs boson is a million times smaller than an atom. So we have this vast range of scales where firstly there's no other candidate story, and we might argue that maybe there's a model, maybe there's not, but there's nothing on the table in front of us that we can actually debate and get our hands dirty with. And I think that the reason there's nothing else is because we've just done it, and we just understand everything we can do at this scale in the universe.
But David, you talk about that scale, but we've also talked about dark energy, and you say that dark energy is real and it's roughly 70% of what's out there. And we know what it does, we know that it spreads through space, we know that it repels, but we don't have a clue what it is. So most of the universe, we don't have a clue what it is.
Actually, it's sort of the other way around. We know too much what it is.
We don't know what it is, we know what it does.
No, there's this horrible, embarrassing fact about physics. And this is just the limit of what we understand and what we don't understand. If you look at quantum mechanics says that at very small distances, everything is random. And even if you look at empty space, there's this small bubbling particles and antiparticles. Even empty space has this soup of quantum stuff floating around. And we know it's there. It's in our theories, we can measure it, and it's just there. If you work out what the effect of this is on the universe, it's dark energy. So we've got this beautiful explanation for it. The trouble is it's a bit too much dark energy.
Go and tell them how much.
It's by a factor of 10 to the 20. 10 to the 120. That's a 1 with 120 zeros. I mean, it's the worst prediction in the history of science. There's something about dark energy we don't understand. That's clear.
I'm
but
not
it's
sure,
there.
but maybe it's just because high-energy physics don't look on foundations in many word interpretation. In many word interpretations, there is no all these bubbles. These bubbles, if you try to measure, if you don't measure, and many words we don't measure anything. There is only one wave. So the measurement, there is no measurement. You mean that all these bubbles, if I'll try to look photon here, or electron, a very short time, very short distance, I will find photons, Higgs, everything. Because I'm not supposed to. There is this to find it, to put a measurement, to put time. All what I say is there is one physical universe, and you say you said there are many infinite number of worlds. It's a question. All these words, it's our concept. It's a part of explaining our experience with physical reality. In physical reality, there is one physical universe. There is one pretty complicated physical world, big wave, entangled. So I think it's relatively economic. Of course, it should explain everything around. And many parallel worlds, which I believe are there. But it's just single physical universe, single physical wave. Without bubbles.
It sounds so simple until you start talking about the many universes that are associated with it, and then it gets a bit more complicated.
It's our stories.
Right?
It's how many stories we can put. We can put many stories in this big book of our physical universe.
Thank you. I'm very glad.